Tokyo. Yeah, as I said, I'm really happy to be in Tokyo for two reasons. First of all, because Japan has a very special place in my heart, and second, because it's very refreshing to be back into a technical meeting. This is a very nice conference, and I really enjoyed it so far. I know it's the last session on a Friday afternoon. I know some of you are jet lagged and some of you are just tired from the week. So don't worry, this talk is going to be an introduction, general introduction on the company. I'm not working on research anymore, unfortunately. I have the easiest job in the company, which is to lead it. I'm the current CEO of Qilimanjaro Quantum Tech, and after me there will be a technical talk from Matthias, which is one of the people in Qilimanjaro that do the real work. But for me now, it's just to introduce you the company or vision and what do we do and why. And I'm used to explain this in a very basic way because usually I'm talking with business people. So I had to change a little bit my storytelling for this conference, and unless anybody has some millions on their pockets that want to invest in our little company, I will explain it in a different way. So no business talk. And the way I wanted to explain it is with my personal journey in the world of physics and how I ended up here, because I think it links very well to the vision that we have in Qilimanjaro on what we want to develop and what we are developing. So I'm going to start with, I'm not that old, but everything started in 2014. So I just finished university and I was working as a researcher. I used to be a chemist. I was working as a computational chemist or quantum chemist on developing new drugs. We were working on simulation of molecules, not very large, because the computational resources were just not enough to take care of them, because we wanted to do the quantum description, not the semi-classical or the classical molecular dynamics description of them. And what we were doing was to explore different molecular candidates to inhibit certain reactions that are related to some uncured diseases. So in our group, we were working with cancer, Alzheimer, and Parkinson. And we were trying many molecules to see if they could inhibit some oxidative components. Here we have methanol. And see if we would find some candidate that would make sense to bring into experimental trials into the lab. And the first step to do this is, of course, doing computational modeling. So what you calculate is the energy differences between the reactant and the product and the transition state, which is what's in the middle, to see if the reaction is energetically favorable. But it takes a lot of resources, and it has a lot of impact in society, but yet we cannot compute it very well with high accuracies or high speeds. So this was the first time I realized that a better way of computing was necessary. And this is what made me shift completely my career and jump into physics, into a PhD in physics, and into quantum computing. But what I'm trying to do here is to show all the applications in which it is really important to have an analog quantum computer. The next thing I worked in during my PhD, I was at the University of York in the UK. I was developing new ideas based on spin networks or spin chains. Spin networks is the two-dimensional version of spin chains. This is a very canonical example or model to study state transfer, localization, and different quantum information processing tasks. Basically, the system is described as a Heisenberg Hamiltonian, or you can use whatever Hamiltonian you want, and then you study you simulate the natural dynamics of it to study different effects. So what we were doing was to invent or come up with entanglement generation protocols that would be useful for communication purposes. not long-distance communication, but short-distance communication between quantum processors, because we wanted to have a generation of an entanglement link that was very robust. And for that, we were using these type of systems. But back then, we didn't have any platform available to simulate this dynamic. So everything was done using classical computers. That's also an analog quantum problem. Then in 2019, I was missing the more hardcore quantum computing programming part, and everybody was talking about quantum error correction. So quantum error correction was and still is the thing. It's what limits us from having fault-tolerant digital quantum computers. So I decided to pursue this route. I actually moved to Japan. I was working at the National Institute of Informatics here in Tokyo at an Emoto Sensei group. And one of my projects was to work on compressing quantum error correction circuits that were having these quantum error correction protocols. And the protocol that we were focusing on is the surface code. Surface code, I'm sure you've heard of it at least once. It's a very complex and complicated error correction protocol, but it's the most standard one. What you do is to, as all the other error correction protocols, you encode your logical quantum information into many physical qubits. And with the surface code, you use stabilizers, and you have a mix between data and ancillary qubits to constantly, repeatedly correct the errors that occur there. And depending on the distance or the size of your code, the number of qubits that you have a better or worse tolerance to errors. But have you ever thought, how do you compute with it? So this is the memory. This is the way you encode the qubit. But when it comes to run a circuit with surface code, it gets even more complex. So there are two ways to developing a circuit in the surface code. One of them is lattice surgery, and the other one is braiding. They are very similar. They are almost equivalent, I would say. I think somebody showed the proof at Google that they are equivalent, but I don't remember. But basically what they do is you perforate your surface or your 2D lattice of physical qubits that represent a logical one. And those perforations are what create you additional logical qubits. So you need to have a very massive 2D lattice with many holes on it that represent your logical qubits. And single qubit gates are trivial with these logical qubits, but 2 qubit gates are not so easy. And one way to do them, and that's what distinguishes lattice surgery with braiding, is the way we do operate with these 2 qubit gates. And the way you do it with braiding, which is what we were focusing on, is by making these defects on the lattice move around and braid between different other defects. So this is how we perform a CNOT gate. And there's no more relevant. I just wanted to introduce the notation because I know it's a bit weird, but the defects on the surface code lattice we represented them as tubes, as these tubes. And the process of making a CNOT is this one, looking at it in 2D. But if we still look at the entire circuit in 2D, so this is an example. So our work was to compress the circuit. This is an example of a circuit. This is a distillation circuit. This is very necessary for fault-tolerant quantum computers. And then we translated it into the 3D representation of the surface code with all the braiding, and we compressed it. We compressed it with one method that we came up with based on ZX calculus. But what I want to show is not the compression technique, which was really good. We got very good reductions on the volume of the circuit. What I want to say is that this is only a part of a distillation. Is just a small part of a much bigger circuit. And if you start looking at how quantum circuit, I don't know, any algorithm that you may come across looks into this representation, you will see something much larger than what you see here. So it's really crazy the amount of qubits and the control and the coherence that you need in order to implement this. And that was very discouraging for me. And this was the time that I realized that quantum error correction and fault-tolerant quantum computers will arrive, because there's a lot of efforts and there's a lot of research, and I'm sure they will find better techniques to do this, but this will take some time. This is not something that will come immediately. So that made me go back to analog, because I was discouraged, and that made me go back to analog. And the other thing that we were exploring after this disappointment was how we could do how we could study interesting phenomena in physics with simulation running on systems that could be constructed with current quantum technology. So in this case, in this work, we were studying time crystals, which is some people consider a new phase of matter. I'm not sure it's exactly a phase of matter that breaks time translation symmetry and space symmetry. And basically, it has some periodicity that goes against the periodicity of the drive. Those are constantly driven systems. And what we did with this was to study the flux dynamics of such time crystals with spin chains. Going back to spin chains. And the other thing that we did was also to try to understand how these systems that are governed by the natural dynamics of its Schrödinger equation, and not so much about the gates of the control that we apply, could be used for other things. So we started thinking a little bit outside the box. And in 2020, there was not OpenAI or ChatGPT or this big boom of artificial intelligence, and we thought this was not so interesting. Now we are taking this back, but we studied how the Hilbert space of a quantum system, of a spin system, could be used as a hidden layer of a neural network for classification tasks. And we saw that this is typically called quantum reservoirs, but it's not exactly quantum reservoirs, because what we were doing was not introducing time-dependent data, and we called it quantum extreme learning machine. It's a funny name. But what you do basically is to exploit this exponentially large space of the Hilbert space to see if the complexity of it can allow you to compress the resources that you need to train very large neural networks. And the preliminary result was that, in fact, you could use this for training. It was not better than classical models, but it wasn't better because we were using a simulation of a quantum system. And something that is very interesting to explore is what happens if you have a very large chip with more qubits than the ones that you can actually simulate in a classical computer, and see if this actually has some advantage against classical models. My intuition is that the advantage doesn't come from the accuracy or the speed of the training of the machine learning model, but more on the resources that it consumes, probably more related into the memory, energy, and so on. Okay, so all of this was to introduce a little bit what changed in the way I looked into quantum computing. So I realized that digital quantum computers are waiting still for quantum error correction. So we have the next devices. They are amazing pieces of architecture, and they have plenty of merit, but I don't believe until we have fault-tolerant quantum computers that we will be able to do widespread applications interesting for the industry. Definitely, we will do a lot of interesting things for research, but something practical for the industry, it will still take some time. And this is just a matter of scaling. the technology or finding the quantum error correction protocols that can sustain platforms that we can actually build, which now is still a bit far away. And then also coming from the realization of all of this, and I know all quantum computing companies like to cite quote, the quote from Feynman. I'm not going to be an exception here. I'm sorry for that, but I'm just doing it because in the same way that he was saying that nature is not classical, but quantum, and if you want an accurate description of it, a quantum computer is a good idea. I like to think that the quantum is not digital either. Quantum is analog. So every time we take an analog problem, a continuous problem, like a chemistry problem or a materials problem, something like that, or a spin chain problem, and we start digitalizing it, we go through a totalization that introduces additional errors. So if we would have a controllable analog, completely programmable machine, this would be the most accurate way of representing the problem. And the other thing, this is something that I found quite curious, that the first applications of computers were in fact coming from analog computers. And if you look at this one from the 1940s, it looks as ugly as our current quantum computers that are very bulky and very complex. Maybe this one is ugliest actually. And they were used for the calculation of flight trajectories and problems that were intrinsically analog. So also thinking that the history tends to repeat itself. What we decided to do in Qilimanjaro is to actually pursue, explore whether quantum analog computers would have an application in a shorter time frame than digital fault-tolerant quantum ones. So this is what we do. Qilimanjaro is a full-stack quantum computing company. We are based in Barcelona. We are in Spain. And we use the analog model of quantum computation. We focus very much on developing chips based on superconducting qubits, but putting special attention on maximizing coherence. So we are doing flux qubits. And another vision that we have on the field is that at the beginning we should, in Spain, you don't start the house out of fully on universal quantum computers, and we think that in the short time space is better to focus on app-specific systems. So let's try to find this application that actually can be very useful to have a quantum computer for, and not trying to cover everything. Let's try to approximate as much as possible the use case with the design and the fabrication of the hardware. You know, it sounds easy to say and it's more difficult than that, but that's a little bit the mindset that we try to have in our team. Okay. And we are a team that does a bit of everything. So we develop end-to-end quantum computers. We have software, theory, hardware, and engineering team that work as close as possible to each other, as close as the intrinsic ties between theorists and experimentalists allow, actually, to do this exercise of co-designing, do this exercise of trying to develop something that is very well integrated. This integration, I think, is crucial in order to maximize the chances of achieving some quantum advantage or something interesting, something that is useful. So we do have this loop that closes and approximates all the application to the software, the development of the software, all the way down to the development of the hardware and back. So it's not the hardware that is available that defines the application, nor the application that we want to solve that defines the hardware. We find each other in the middle. And this is a little bit the stack that we work on. So when we say full stack, this means that you work on each layer, going from very low physical layer all the way up to the more abstract layer, which is the application. So there's one higher layer that has nothing to do with quantum, which is the access and the web user interface. So if people want to connect to the quantum computer, they need to have a way to reliably do that. It needs to be scalable, it needs to be secure, and it needs to be easy to use. And then we have also an algorithm portfolio, but we develop, we reconnect all the algorithms that we build in the company by an applications team. We have a programming framework because you need to program your quantum computers in a specific language. This is a language that is called Kibo. It's an open source quantum computing language that was originated in Qilimanjaro, and now it's a global effort with many institutions collaborating to it. Then we have the hardware control, which is nothing more than the operative system, but that's actually a very complex part of it. So developing a good software, a good control software for the hardware is a crucial part of having a success story on a quantum computer that actually works and that you can run something. So the software part, even though it's not an intrinsically quantum thing, is very crucial in this stack. And then, of course, control electronics and setup integration, which is what puts everything together. But the core of this stack are the backends. So what are the quantum platforms that we connect to? And we believe in hybridization. We think quantum computing won't be a standalone thing. I don't think we will see like a quantum computer in a company that they use like really isolated. That's practical. We will see this hybrid and connected to supercomputers, like an accelerator, as we see now, GPUs accelerating CPUs. And in the same way, I think we will see them hybridized into different models or even different architectures, because not all architectures work the same things. So with this in mind, what we do is to focus on digital quantum computers, digital QPUs. We know we have the knowledge on how to fabricate them and how to design them. We've done it in the past, but this is generally not on bigger efforts. Our efforts are on the design and fabrication of analog QPUs, because this is where our IP relies to. And we also have classical simulators for network networks and so on. And we pack everything together to provide access to it. And this is our offer. So what we do in Qilimanjaro is this type that you've seen, but then we sell it, or we provide access to it, or we make it use in different manners. One of them is as a cloud service, quantum as a service, which we think is the most usable ones for the users. We are not talking only about industry users, but also universities and research centers that, I mean, if I had this type of access when I was working with spin chains, I would have been amazed. So even if you cannot provide a quantum advantage, you can do very nice experiments with it in the short time range. And then the deployment of the system. So there are some people, some institutions that actually want to buy a quantum computer, and we can do that. So we've actually done it, and we keep doing it. We pack everything together and we bring it into your house. The type of clients that ask us to integrate the quantum computer in their house are HPC centers and research centers. Industry companies are asking for that, at least to us for now. And this is actually one example on this type of project. So I don't know if you know the Barcelona Superconducting Center. It's one of the largest HPC centers in the world, and it has now a very famous supercomputer that is called Marta 5. And one of the particularities of this research center or supercomputing center is research. So you can say, I don't know, we wanted a computer. So Qilimanjaro is providing them with one. Actually, they already have access to. But in this month or next month, I'm not sure when it will be finished, the quantum computers will also be inside this church. So it will be the first quantum computer inside the church. And then the quantum as a service is the platform that we want to provide access to. And as you can see, it's not ready because you can see many failed jobs, 642 jobs. We are still working on implementing the platform and putting everything together. But it will be ready very soon. And actually, we want to release it to the public next year. And this year, we're looking for what we call beta testers. So if anybody would like to try it for free for a certain amount of time in exchange of feedback, we'll be happy to create you an account. Just try it. Because what we want to do first, and we think is very important, is to get scientific validation. So I'm going to explain this later. We don't want to sell small. We want to sell something that is really useful. Okay, I'm going back to the usefulness, applications of quantum computing. So there's one thing, that is analog quantum computing goes much beyond quantum annealing. So there are more things that you can do than quantum annealing. Quantum annealing is an algorithm, I would say, that you can run in an analog quantum computer, but there are other things that you can do. And one thing that we try to defend all the time is what I was saying, that we don't want to sell smoke. Industry applications of analog quantum computing or quantum computing in general are not there yet, And I think there's been a lot of hype and a lot of irresponsibility in making the community believe that there's something, but there's not something. And I'm sure in a few years we will see a much more advanced technology, but it's still not there. And we need to work to advance it. So I think optimization problems are really a very potential application of quantum computing, especially analog quantum computers, but we cannot really run them yet. I mean, the problems in optimization that become really interesting for the industries are such that they have thousands and thousands of variables and many constraints. And when you map this into a cubo, it's so big that you might as well have a fault-tolerant quantum computer. So we need to be we need to be honest with that. This will take still some time, but this doesn't mean that we cannot do interesting stuff within this range. And one thing are quantum-inspired problems that require zero quantum hardware, but it's funny to see that just thinking differently on how you can build algorithms, you can actually provide some speed up or some advantage in certain tasks. Then you have AI and quantum information processing. This is something that you can start doing with very small chips. You can start exploring how you can do certain tasks or how you can invent different ideas. This is very relevant for researchers, I would say, in the quantum industry, and of course the simulation part of things. So you can, if you have a certain size of chips and you run a simulation on it, that's something that you can't really replicate with a classical computer, because if you go beyond 30, 40 qubits, that's already too difficult to simulate. And we saw that, by the way, on the first day with Mohamed Amin's talk, where they were doing simulation with their D-Waves machine. Okay, so what do we work in terms of applications? And I'm not going to say quantum computing, but quantum inspired, is to develop algorithms in certain verticals that are that could potentially be interested in quantum computing, like energy, chemistry, finance, logistics. I'm sure many of you have touched this type of use cases and problems because they tend to be very close to optimization problems that can translate into QaaS. So we want to really study them very much. So we develop different algorithms based on tensor networks, based on different simulation models, classical models, and different simulators. For instance, we've tried the digital annealers of Fujitsu, or we've tried also different platforms that actually can provide you some nice results for this type of problem. So I know there's a lot of people that do not want to hear about quantum-inspired algorithms, but at the end of the day, this is nothing more than trying to improve the algorithms that already exist. And as long as they are helpful, why not? So we work on this because it also allows us to understand real use cases that people are pretend. If we are blinded and we only think about physics or about chemistry or about what we've learned in our research groups, then we don't really see why this technology could be interesting to the outside world. So it's really important to be connected with the industry as well. And for the simulation, I will let Matthias explain an example. I'm giving a bit of examples of what we are doing. And for the simulation side, I'll let Matthias show one interesting example on fermionic simulation. For AI, what we are doing is also try to identify problems that are interesting for somebody. So not just doing random classification. And there's this one, I don't know if you know, the Hyperkamiokande project is happening actually in Japan. It's going to be it's going to start recollecting data in 2027, and I think is in Gifu and Ibaraki prefecture. And what this huge detector is planning to do is to study the biggest in the world. And we're in collaboration with CERN in Geneva 5, which is another institute of high energy physics, to develop algorithms, either classical or quantum, that can help in the classification of the different events that the detectors of this Hyperkamiokande receive. So they can receive a lot of data, and this data can be linked to different high energy physics, particle physics events, like this one, classifying them. And for that, they use machine learning and very complex algorithms. And one thing that we want to explore is whether we could use a quantum algorithm to make it more efficient. I mean, not now, of course, but in the future. And in the same way, in the same fashion, we collaborate with CERN on the track reconstruction problem. The track reconstruction problem is the problem that consists on completing a path that is followed by different particles when collide in the Atlas project that they have running there, which is also a very complex problem. And what we are exploring here is precisely whether an analog quantum computer would be useful for this classification problems. And then we don't only look at use cases, but we also look into the future. So we try to resolve some of the limitations that are actually present in current devices and algorithms in order to be able to get closer to this practical use of quantum computers, for instance, for optimization problems. So two big problems of QaaS problems are two big challenges are the connectivity of the device. So when you have a planar chip, your connectivity is quite constrained. But at the same time, your QaaS problem is represented by a graph that can have arbitrary connectivity. So every time you have to map this graph into your device, you have an overhead, computational overhead for finding the right embedding. This is the graph embedding problem. And this is actually something that if you've used Z-Wave, you struggle with, because they have a strict connectivity. It's not a full connectivity, and they have this Chimera and Pegasus graph, but it's not a full connectivity. So you have to map one graph, one topology to the other, and that's not always very trivial. So one way to do that is, I don't know if you heard the LHZ scheme. The LHZ scheme is a chip architecture that allows you to have this all-to-all connectivity by at the expense of putting cancellers and 4-body couplers. But 4-body couplers are not very easy to fabricate and control. So that's not something that is easy to implement either. So what we did with Ana Palacios, which is another colleague of us, is to develop this architecture that allows you to have this all-to-all effective connectivity in your chip without 4-body couplers. And in the same fashion of solving problems and challenges on optimization for quantum is the correct assignment of the penalty terms that you put on your constraints. So this is not always easy to identify which are the right scalars that you have to put there in order to make the problem work. And those are also called the Lagrange multipliers. And what we are studying is how we can use a method called graph neural networks, which is a machine learning algorithm to automatically assign these Lagrange multipliers in order to construct the Kubo problem in a more efficient manner. And so far the results are quite good. So here you can see that no matter how big the Kubo problem is, you converge more or less at the same point. So the different colors are the size of the problem. Okay, so that's a little bit the use case. Then go jump into the software. There's not much to say here, other than that what I already said. You need a language. You need a language to express your problems. So we had to create a language, and then you need an operating system. You need an API that is able to translate the high description of your algorithm into a low description that your chip can understand, which is typically based on pulses, a sequence of pulses, at least with superconducting qubits. And then we have the chips. So we develop and control digital QPUs, but mainly our idea or focus is on these analog flux-based QPUs. So that's one of the first ingredients and conditions of the hardware we developed. We work with flux qubits. The other one is that we focus very much on architectures that maximize coherence. We think that having long coherence times is a must if you want to do analog computing or annealing. And we think that this is what constrains the applicability of quantum annealers. So we focus more on the quality over the quantity. So often they ask us, how many qubits do you have? So I'm going to be honest, we don't have that many. But because we really focus on iterating a lot on the design of them in order to maximize this trick, because otherwise it doesn't really make sense to scale up. You don't have good quality qubits. And finally, something that we are working on is on new designs in order to have couplings between the qubits that go beyond the effective ZZ interaction. So with this, you can build systems that are not just Ising models, but something that is more complex, like a Heisenberg model. The tricky bit, spoiler, is to independently tune these couplers, and that's what we are working on at the moment. But if we manage to do that, then we would have a very nice platform where to encode arbitrary quantum problems, and that's the goal. And just to show you a little bit one of our designs, this is one of our single qubit designs. The C-shunt flux has Z and X control. And you can see here some of the measures of the coherence times. T1 is 1.5 microseconds here, and T2 is 160 nanoseconds. So the coherences are quite good. And what we are working on now is to make them even better by iterating a lot on this design. So if you, I think you don't have the posters anymore, but I was about to refer to David Lopez, another colleague of us, a poster who was actually presenting this architecture today in this conference. Sorry. And last, I'm finishing with this, just to comment on our team. We are currently 51 people, most of us physicists, and growing. And we have also a lot of students, so if we count them all, we are around 60 something. And this is our brand new lab. We just moved to a new space in the city center of Barcelona. So if you ever come to Barcelona, you want to visit, you are welcome to come. Just drop us an email. We love to make visits in the lab. Now, at the moment, we have here 2 fridges because we are still moving from the old one. And at the end of the year, we'll have 2 more. And next year, 2 more as well. So we are populating the space as fast as we can. Okay, and this leads me to the end. Summary is just a bit of the conclusion, and the message I wanted to bring is that we are just at the beginning of a very promising field, but that asks for responsibility in the messages we deliver. And I believe full-tolerant digital quantum computers are still far away, so we need to be conscious about that and see what we can do in the meantime, because I think we can do many things, but this requires to start thinking a bit outside the box, to not follow the same ideas that have been established long ago, and start thinking what we can do with what we have, and recognize that quantum computing might not be useful, at least at the moment, for what we originally thought, and that we might need to find new applications. And also the message that we really need to focus on improving the basic elements of the hardware before scaling up. So it doesn't make sense to keep competing about how big is your chip until you have a chip that has a basic element that works. So the improving of the qubits, and we had a very nice talk just right before, the improving of the qubits is really essential, and as well as the control and everything that surrounds it. And finally, I think analog quantum computing is much less explored than digital, and I think we will see interesting applications coming up in a short time frame.
Okay, Isu. Thank you very much for this nice talk. Just a question about one of the applications that you comment. So for the neutrino experiment, so the problem is that you cannot store all the data, and then you have to classify them before you run out of memory. Is this kind of issue?
I think the problem that they have is that I think one of the users of larger computational resources is CERN and the high energy physics and particle physics community, because they really have very complex problems to solve. They have a lot of data that they have to process, and that basically makes them. I'm not a particle physicist, so I'm not really sure why do they need that. But as far as I know, they makes them have huge machine learning models that require a lot of processing and a lot of memory resources. So they are good models, so the solutions that they give actually are very accurate. I don't think it's a matter of accuracy, but they take a lot of time, and especially they take a lot of resources. So what they are looking for is to compact, to compress this a little bit more. And if the idea of exploiting the Hilbert space of a quantum system helps reducing this, because I mean, with 10 qubits you already have to the end nodes that you could use as hidden layer of your neural network, then that would be very advantageous for this type of application.
Is there any other question? Thank you. One more, please.
big again.